All right. Yeah, let me go to the whiteboard here. So, right. So Caroline's question was, right. That was, yeah. So yeah, it looks weird because it's in this bicyclic system where everything's tied up. But there's going to be enough flexibility to do the usual kind of rearrangement. So in the first part of the first step, what occurs?
Basically, you're going to have the double bond go to the like oxygen with like two lone pairs, then the double bond between the oxygen is going to go to the like positively charged oxygen, and the negatively charged oxygen is going to go to like one of the carbons.
Yeah, exactly. So you got something like this, right? There's my ozone. And we can have pi bond attack, and we can push electrons in, and then we're going to have these electrons come down. And so carbon skeleton doesn't change, so I'll redraw the intermediate here. So I've got O, O, O. Okay, right?
And like in real life, like the cyclopentene thing would be like kind of in the plane of the page, and like the oxygens would like almost be coming towards you, if that makes sense.
Yeah, they'd actually be going back a little bit. Yeah,
Okay.
I could draw it with perspective. It'd be something like this. So it'd be sort of, I don't know if that helps, but
Yeah, that does. Okay, so basically like the pentene rings would be kind of like, it almost would be trigonal pyramidal in some ways.
yeah, close to tetrahedral. Not going to be perfect, but yeah, because it's basically that O3 is going to come down on top of the alkene, and when you make that 5-membered ring with the 3 oxygens, you sort of push those 2 flaps that are the carbon containing down. Yeah.
Okay.
Let me see. I can plug it into Spartan too, which is kind of cool. Let me just plug it into Spartan for you real quick. All right. Let me share on my computer. Share screen. Yeah, so you can see it there.
Oh, okay. That's pretty cool.
Yeah, so it basically pushes those 2 rings down, and these carbons where the oxygens are attached are almost tetrahedral. They're not. It's not quite perfect because of the rings, but
Yeah.
Gives you an idea. Okay. All right. So so then second step. So
I can't see your screen. I don't know if you're, oh, now I can.
there we go. Did I lose all the whiteboards? Shoot. All right. Well, that's okay. It's recorded, but let me just, so we're going to make that molecule. Okay. And then what's the second step?
Then basically you're going to have like a bond between the like central oxygen cleaved, and then like a double bond formed.
Yeah. Yeah. So we're going to, this is the primary ozonide, right? And so we're going to decompose that. And so you can take the electrons in the CC sigma bond, push them up, take the electrons in this OO bond, push them to that oxygen. I can't go to the next oxygen because I have 8 electrons around there.
Yeah.
And then I can take, well, let me leave it like that for a second, just to keep it simple. So then we will get something like this. Okay. And again, strategy is move as little as possible. So we're just going to put this right here, even though it looks a little odd. And this we're going to draw down here. And this one has 2 lone pairs, right?
Yep.
I've broken that central CC bond, so I have a positive charge on this carbon.
Mhm.
Okay. And then we can draw out the other one with its negative charge. Okay. And then, you know, what we've done, I think what I did in class was I drew directly a resonance structure where this oxygen lone pair is donating in to the carbon. And so you have something like that, right? Yeah.
Yeah.
So you can go, when you're drawing the mechanism, you can go sort of with the blue arrows, or you can go, you know, if you want to do 3 arrows, you can go basically bang, 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 and then get directed to that other resonance structure. Okay, so then the question is what happens? And I guess, you know, would help if we had a model, but you can flip that carbon. Okay.
So basically you're even though it's in the ring, you're like like almost if it was like a pencil, you're like turning it that way, if that makes sense.
Yeah, exactly.
Okay.
Exactly. So, you know, so if we imagine that all 3 oxygens are up in that initial cycloaddition,
Yeah.
and we're gonna say, okay, nothing's changing geometries yet. Okay, so let me redraw it with that perspective in 3D. Okay, I don't know if that, hopefully that helps, but basically the rings are like this, and then the oxygens are coming up.
Yep.
Okay, and then, yeah, so what I'm going to do is just pick one of them and swing it down, you know, by 180 degrees. So if the oxygen's up here, I'm just going to take it and rotate it down.
Okay.
And then that's what allows me, and again, yeah, you know, this is hard to see in these kind of these 2-dimensional things. It looks, you know, but that will get me to a structure like this. So I have to kind of, it's going to look a little weird, but you'll trust me when I, it ends up looking something like that. So these bonds are crossed over in front. Okay. And then you've got the carbonyl in the back. And so then I can do the combination, and it's not, you know, there's no real bending or gymnastics to do it. So then you can basically have this guy come up here, and then this one comes up on the bottom in the back.
Okay. And then what does that look like? Sorry, I'm just having a bit of like
Yeah. So it looks like this. So yeah, what does that look like? It's a good question. So it's going to look like this. So it's going to be basically bang, 3 carbon bridge, 3 carbon bridge here, and then 2 oxygens down.
Okay, and this might be like a dumb question, but like I guess what I don't get, and this is kind of more fundamental, like how is what we have like up on the top left different from what's on the bottom left?
Connectivity. So
Oh, so it's because on the top left there's a carbon bond in between, and on the bottom one there isn't.
yeah, and the bonding to the oxygens has changed, right?
Oh, because in the middle one or on the bottom one, it's like you have like the three oxygens in like a kind of closed ring, if that makes sense. But there's no, like, obviously there's like other carbon attachments, but like they're not really attached to carbon, like in between oxygen, if
Yeah,
that makes
there's
sense.
no, so that central CC bond is totally gone. And then if you just consider look at the O connectivity. So I've got O bonded to O bonded to O,
Yeah.
right? And on the bottom, I've got O bonded to O, but then I go to carbon, back to O, to carbon.
Okay.
So
Okay.
let me draw a simple one in 2 dimensions, because maybe that'll help to just see the direct comparison. So you have the top one, forgetting about the other rings, is kind of like that, and the bottom one is going to be so C, getting in trouble with the colors here, O, O, and there's a carbon here. So A, B, A, B, and then call this A prime, B prime, A prime, B prime. I don't know if that, does that help?
Yes, okay. I think I wasn't getting that like more fundamentally, like why the rearrangement happened. Okay, and then once that rearrangement happens, is then when you do the kind of quote unquote attack from the dimethyl sulfide.
Exactly. Yeah. So this is what
Okay.
forms in solution. So this is ultimately what you're going to have in the pot before you add the reductant, dimethyl sulfide, whatever you're using. Okay.
Okay.
And
Okay.
the reason it happens is because this primary ozonide on the top left here, if you think about it, I've got an O, O, O linkage, right?
Yeah.
And, to be fair, we haven't discussed this at all, but, just in a peroxide, you're looking at 33, 36 kcals per mole for an OO bond. The
Hmm.
O linkage, I don't know what it is. Someone's probably calculated it, but it's got to be even lower. Like
Okay.
basically those bonds are very weak.
Okay.
And so, it's a good, because this ties nicely into what we're talking about today. We were talking, you got to put 85 kcals in, 90 kcals in to break a CH bond, right? If we're saying, okay, an OO bond in a peroxide is 36, and this sort of trioxides, each of those OO bonds is probably lower, let's call it like 25. That's, you got about 15, 18 kcals at room temperature. Like, so
Hmm.
it's very close to basically not being a bond. Like, it's just super weak. And so these things just fall apart, doesn't cost you a lot. And then it can recombine to get to this rearranged ozonide. And now I've gotten rid of that trioxide linkage. I still have my peroxide, which is a weak bond, but I don't have this really sort of, esoteric O linkage. The system's more stable.
Okay.
And then that'll sit around till you can reduce it. Yeah.
And then can you show how the like dimethyl sulfide would then attack, like at least in this system? Just because
Yeah.
like the
So
textbook showed the final product and like, but I don't get how you get to the final product, if that makes sense.
yeah, yeah. So the important thing to remember is that you want to attack the peroxide with the reductant. And the reason is that again, that OO bond is the weakest bond in the system. Okay.
Mhm.
And so let me go to another little bit here. So if we have our rearranged ozonide, okay, like that. And
Mhm.
so, so if I'm going to attack an oxygen, right, those oxygens already have an octet. And so I'm going to need to break a bond so I don't violate the octet rule. So then the analysis is, okay, I need to break a bond. That always costs energy. So what's the weakest bond? What's going to cost me the least amount?
That's gonna be the OO
That's
bond.
the OO bond, exactly. So you have S come in. Okay, we can take a lone pair on sulfur, attack oxygen.
Mhm.
Can't violate the octet rule, break the OO bond.
Okay.
And again, you don't know these numbers and we don't expect you to at this
Yeah,
point,
of course.
but you can back of the envelope calculate it. We can say, okay, so OO bond 36 kcals per mole, SO bond, I don't even know what that is. Let me see, it's got to be at least 100. See if it's on my table here. Yeah, SO bond, okay, 93. Okay, so 36 minus 93 is whatever, 57. Something,
Yeah.
right? So negative 50. So you're downhill by 57 kcals per mole. So that step is enthopically is very favorable. And
Okay.
so what you end up with then is let me redraw it here. Is an intermediate like that. Okay.
Mhm.
It's important. You got to balance the charges. So plus on sulfur,
Yeah.
oxygen, right? No charge going in, can't have any charge coming out. And then, so you want to see the collapse?
Yeah.
Yeah. So it may be helpful for this when you're doing these types of ozonolyses, complex substrates. Don't be afraid to like unpack the reaction and do things in little digestible bits.
Okay.
So as long as you're not breaking, basically the octet rule, you're fine. So first bit is going to be, I'm going to take a lone pair from this oxygen in the back here and push them down to the carbon that's in the back. So hopefully you can see that.
Yeah.
Okay. And then I got 10 electrons on there. So I need to break a bond.
You're gonna have the one between the oxygen and that carbon break.
Yeah, exactly. Push those up.
Okay.
So you could keep going, but I think for the sake of clarity, it's okay to just stop and draw another structure. Okay.
Okay.
And so OS, still got the positive charge on S. That hasn't done anything, right?
Mhm.
And then in my back side, I've got double bond to carbon.
Okay.
And then, and again, also the other suggestion is, number your atoms. So 1, 2, 3, 4, 5, 6, 7, 8, 9. That can be helpful, and so I have 3 carbon spacer here. 1, that's 4.
I think there should only be 8 carbons, but it's not really important.
Did I miss something? 1, 2. Oh yeah, I stuck an extra carbon in here. 1, 2, 3. This structure is okay. This structure, let me just clean this up real quick. it's like that. Yeah.
Yeah.
So so 2, 3, 4, 5, 6, 7. There we go. Yeah, because I remember I emailed you this was an octene. Yeah. All right. So we can start connecting. So basically, bang. 1, 2, 3. Okay. And again, if you're starting to lose track, just put numbers in. That helps to keep everything, you know,
Mhm.
in place. So we've got carbon 4. So this is carbon 5. And I see from my left structure that carbon 5 now has a CO double bond. So that looks good. And then I need to go out. And I've got carbon 6, 7, and 8. So this bond in the back, this is in the back here.
Yeah.
Obviously,
Okay.
this is
And
terrible,
then
terrible drawing. It's not those.
and then basically from there you would push the negative charge to make a double bond, and then you would push the single bond to become a leaving group.
Exactly. Yeah.
Okay.
So you just push this down, push that down. And
Okay.
so you get basically this diketone product. So let me see if I can redraw it a little bit better here. Okay.
Okay.
And then numbering again, 1, 2, 3, 4, 5, 6, 7, 8. And then the byproduct is
The sulfur methyl oxide or whatever it's called.
yeah, DMSO. So you probably use this in lab. It's very common solvent, dimethyl sulfoxide. Yeah, so that leaves, and then that's all she wrote. And this one, because you don't have an H attached to the alkene that you began with, right? Oxidative conditions give you the same product.
Okay.
You know, and so you can work through the mechanism there. It's going to be very similar, except you're going to have water behaving as nucleophile in this step. Okay. Yeah.
Okay, so I'll try the oxidative process at home and
Yeah. If you want to chat more, we can follow up. Yeah. Okay.
Thank you so much, Professor Herzon. Have a great day.
All right. See you Friday, Caroline.
I have a quick question about today's lecture. So when you were talking about, sorry, let me just reference my notes. So I just want to understand, like, specifically, like, in certain situations, like why we would use like the regular calculations where it's just like start to finish, what is the change in enthalpy versus like how would you know to like go ahead and check for the individual steps, or like would you just tell us like this reaction doesn't actually happen, explain why, and then we know to, based off of like what we discussed, to go ahead and like do the individual calculations for each of the steps?
So I don't know how exactly we'd frame the question, but you know, I think it sounds like you kind of have the general idea, which is that the overall delta H for a reaction, okay, it's sort of like it is it is necessary but insufficient for the delta H to be negative for a reaction to occur. Okay. So if the delta H is positive, again, there are exceptions, but most likely the reaction is not going to go. Okay. So if the delta H is negative, then that's kind of like the first litmus test. You know what I mean?
Mm-hmm. Right.
And then, so that's like, it can or cannot happen. You know, the law, you know, the laws of the universe say it's okay or it's not, you know? And then, but then the second test looking at the individual steps, that's asking the question sort of, how fast is this going to happen? You know?
Right.
And
Okay.
yeah, does that,
So yeah. I think it makes sense, but I'm just wondering, like, so is it that in every case where we're asked to decide whether, you know, based off of these enthalpies or the bond association energies, like, would it be the case that we do have to go through both of the steps? Because like, I think maybe the way that I understood it at first was like, here's the one way to do it, and then here's the second way. But is it that it's a process to figure out, and we always have to check them? Like, I'm just trying to figure out, like, generally when we think about reactions, are we checking, are we using both of the like litmus tests to decide whether it actually happens or not?
I hope this answers your question, but it depends on what information you want. You know what I'm saying? So if we want to know outright if the reaction can occur, then you want to look at the total delta H. But if you're just asking the question, you know, how fast does this occur? Delta H doesn't tell you anything about that, the overall delta H. Then you need to look at those individual steps. And so the way to analyze it kind of depends on the information that is required. Hey, did you get it off? Hey. Sorry, one sec.
Looks like we have commodity protection at most.
Okay.
We're probably gonna have to step it up.
Did it decompose at all or no?
It looks like there's like less and less of it in it.
I see.
Like, especially this morning after I left to go over at 60.
Okay.
So my guess is
All right. I'll follow up with you. Yeah. So it depends on what information you're asking for. So if we ask about the overall reaction, you know, is this reaction enthopically favorable or unfavorable? That's delta H reaction. If we say something like, you know, is this reaction or explain, you know, why you know, this reaction has a negative delta H, but still doesn't occur. Here are the delta H's for all the bonds. You know what I'm saying? Like that would be when you would start to look at the individual steps. So the analysis depends on what type of information you're seeking. The overall delta H tells you whether or not it can occur. The individual delta H's sort of tell you if it will occur. That helps.
Okay, yeah, I think that does help. And Christine, if you want to go ahead and ask your question, because I have a couple of questions.
Oh yeah, totally. Thanks. Yeah, no, so I had a question just from like the very beginning. So like going back to the thing I was asking in class. So I was a little confused because I had thought that we had talked about how the less hindered radical is preferred, but like then when we saw that secondary alkyl radical is preferred, I was just kind of confused as to why that was if it's not less hindered.
Yeah, no. So forget that first part. That is, I think what's probably happened is you kind of crossed two circuits there. So attack at the less hindered carbon is favored.
Oh, got
Yeah.
it. Okay.
But attack at the less hindered carbon leads to the more substituted, or you could say the more hindered radical.
Okay, so then attack like the BR attacks, or like the halogen attacks at the, is it a halogen? So a halogen attacks at the less hindered
Exactly.
carbon.
Yeah, or dot, CL dot, whatever.
Mm-hmm.
That comes into the less hindered carbon. And then, you know, if you have the flow of electrons correct there, you end up making a CBr bond to the less hindered carbon. But then you have to do something with that remaining electron in the pi bond. And so we stick that on the internal carbon. Okay. And so let me just draw it down here. So attack of bromide at the less hindered carbon. Okay, so I'm going to make a CBr bond right there. I'm taking one electron from the pi bond to make the CBr bond, and that leaves one behind. Excuse me. So I need to push that over. And so then what you end up with is bang, CH3. So this is the more substituted radical, which is more stable, arising from attack at the less substituted carbon.
Oh, okay. Got it.
Hopefully that, yeah, hopefully that
No,
helps.
that definitely cleared it up. Thank
Yeah.
you. Oh,
Because there were two factors, I think, I mean, so there, the main factor is radical stability. That's actually the most important, but the other factor is this kinetic issue of how accessible the carbon is. And so, the attack at bromide at the less hindered carbon, forgetting about radical stability, is going to be faster, okay? And the radical stability trend is mutually reinforcing with that trend. So attack at the less hindered carbon generates the more substituted radical. That radical is more stable than the other one. And so it's sort of those two things working together that drive the pathway.
okay. Got it.
Cool.
Thank you. And
Yeah.
then also I just well, wait, okay. I mean, I'll ask this after, but because the thing I wanted to ask if you would ready to go back. I missed a few things in the slide, but like one thing I missed on the slide was that when you talked about like RHR, the type, and like the bond association energies, like I missed that like last part that like I just didn't get to write it down.
Okay.
That's so I can copy it down.
Yeah, I lost all the slides here because I stopped recording, but
Oh, got it.
it's uploaded like as soon as we get off here. Yeah.
Okay, okay.
So you can just scroll through it online.
Oh, okay, got it. Thank you. And then another question I had was I'm just kind of unsure about how the like delta H is playing. Sorry if this was already asked already, but how delta H is like playing a role with the whole radical thing. Like when you were doing that, when we were going over that chart at the end, or the energy diagram at the end, I just wasn't quite sure like what it was showing, like in
Yeah.
in the context of radicals.
Yeah. So what I was basically doing in that chart, and again, yeah, I wish I had it with here, but we're basically showing. Do you have it in front of you? You have your notes in front of you?
Yeah.
Okay. So on the left, we've got, on the very left of that chart, we've got Br dot plus the alkene, right?
Mm-hmm.
And then in the center, we have the alkyl radical intermediate plus HBr. And I'm just referring to the HBr pathway for now, right?
Yeah.
So what that is showing is that first step, which actually I've drawn here at the bottom, which is the attack of the bromide radical on the alkene. Okay. And the salient sort of information in that chart is that the difference in height between the Br dot plus the alkene, which I designated with that little horizontal line, and then the alkyl radical and HBr also has a horizontal line. That difference, okay, is the delta H for that step.
So like like the beginning horizontal line, and then the one that's after the hump, I guess you can call it, after the peak.
Yeah, after the hump. Yeah, exactly.
Okay.
So it's a complicated diagram because then we have two pathways on the same diagram. But yeah, so the first horizontal line, and then if you just follow the line going from that over the hump down to your first horizontal line, okay,
Mhm.
that sequence corresponds to this first step. And the difference in height, which I was showing with the red double-ended arrows, that's the delta H for that individual step. And so, yeah, so you could arrive at that yourself if we wanted to figure out the delta H for the first step. It would be bonds breaking minus bonds formed, right? And you can do this for any step. It's we can do it. You don't. It's a legitimate calculation for a whole reaction. It's a legitimate calculation for a reaction that has 20 steps for one that has one. And we can calculate each step of a 20-step reaction or each step of a 2-step reaction, whatever you want to do. It's totally like legal, if that makes sense. And so I can do that delta H calculation, broken minus formed. And so in the first step, what's breaking? You tell me.
The CH, the alkene.
Yeah, pi CC,
Yeah.
right? I retain the sigma bond, but the pi bond is what breaks. And then what forms?
The bond between Cl and the C, so a sigma Cl bond.
Yeah, the sigma carbon halogen bond. So go to the table, look those up, do the subtraction. That gives you the delta H for that individual step. That calculation is done. Okay?
Yeah.
And then you can go and do that for the second step, but you treat it as like a fresh, it's a fresh calculation. So we don't think about anything, we don't worry about anything that happened in the first step. Now for the second step, I'm starting with my alkyl radical. And then if we go, say, the chloride pathway, the alkyl radical is going to attack HCl. And I'm going to form product. And this is now all the way on the right of the chart. Form product plus Cl dot. So it's the same calculation, breaking minus making. And so what's breaking in that step?
Wait, you're talking about the second step of this, right?
Yeah. Second step.
Right. The bond. Is there? I don't know. Is it the HCl?
Yeah.
Is the HCl breaking? Oh.
Yeah. Right.
Yeah.
So again, don't let all the details like throw you off. If you get stuck with this, like extricate it from the entire, diagram or reaction pathway or whatever. So, so what's happening in the second step? Oh, I'm not sure. Okay, well, I know I've got my starting materials here in the center in this case. I've got my alkyl radical plus Cl plus HCl, right? And then I've got my product all the way on the right, the final product of addition of HCl plus chloride dot, right? Like just pull those out and like redraw them. You know what I'm saying? So you can see them clearly without any of this other stuff going on. Yeah, and then just ask the question, what breaks, what forms? And that's your delta H.
Okay, so it's like you can find so like after you do each step, you can add that difference together to get like the total delta H.
Exactly. Yeah,
Okay.
yeah. If I did the math right, it should all line up to give you the overall delta H for the reaction. Yeah.
Okay, so I could do like bonds break minus bonds form for the first step, and then plus bonds break minus bonds form for the second step.
Precisely.
Okay, awesome.
Yeah, yeah. You get yeah. That should get you to the same number.
Okay, thank you.
So another question that I had was, so I was doing the sapling and there was just like a a halohydride formation question. Is that, yeah. And basically they didn't write out like that there was or did they? I don't know. But they didn't include water. And so I was wondering like if it was implied like when it's not included, if you're adding like you know, BR to like an alkene, but there's no like solvent. I
Yeah.
was wondering if you just assume that there is one.
Did they specifically say like halohydrin?
No, they
Okay,
said predict your products of the reaction, ignore stereochemistry, include hydrogen atoms in your structure.
okay. And then so they just drew, tell me what they drew out.
They drew what is it, propene, butene, and then plus BR, and then an arrow, and then we had to draw the product or the
Okay.
major product.
Yeah, it's a good question. So this is a good rule of thumb is that any reactant that ends up in the products, even if it's used as solvent like water, you know, I think there are also some questions about methanol in the text. That needs to be shown explicitly. And so if they haven't indicated a solvent, I would assume that there's no water in the reaction.
Okay.
Does that answer your question?
Well, I mean, so I kind of just used, I kind of assumed that there was water, and then I just got the answer that they asked for. And so in the solution that they show,
Yeah.
it's kind of the same process, like with the with that like structure, like that pyramidal, or not like pyramidal, but like that when bromine is like bonded to the two carbons.
Mhm.
So to me, it looks like the halohydrin formation, but they're just not saying that water is there. But definitely on an exam, you would have like, this is the solvent used, or
Yeah.
if there is one.
Yeah, I mean,
Okay.
if the solvent were involved, if basically forget that water's the solvent, like if water were adding, if water were participating, if methanol were participating, that would be explicitly shown or said. Yeah, it sounds like they just kind of goofed a little on the sapling.
Okay, and then also, so kind of going along with this, I was wondering how we could tell whether something, like there are like clear indicators that like of like solvents that are like participating, you know, like if it's like a strong acid or like, you know, where water in the presence of a strong acid. So like I was wondering for like for instance, you wrote out like in lecture when you're talking about the addition of the like halogens, like you use like CH2Cl2, and you told this is a non-participating solvent. Is there like other ones that we should know just like offhand? Like I don't remember exactly if this was a question on
Mhm.
sapling, but I feel like, oh yeah, so like there was like an alcohol, right? So in the presence of a halogen. So is that also an example of a non-participatory solvent, or
So to the first part of your question, the choice of solvents, I actually remember this when I took this class when I was in your situation, because it's kind of like, why are these people throwing these solvents out here, and when do you pick what? Don't worry about that for now. That's solvent is basically it's a function of the type of reaction that you're running, the temperature you need to hit, the solubility of the reactants. It's one of these things that just, if you go and work in an organic lab, you'll get it in a week, but it just takes sort of practical knowledge of what you're doing. but what you do need to know, so there's no need to learn a list of solvents, but what you do need to know is if a solvent is able to participate in a reaction, and that's important for things like this, halohydrin formation where water comes in, right? And so you sort of need to, and again, I don't have a great answer for this, but you sort of need to be able to generalize the reactivity that you see with water in like a halohydrin forming reaction to say like methanol, so CH3OH. In that reaction with bromine, you would get a methyl ether as opposed to an alcohol in the product. So it's kind of understanding, not, what I don't want you to do is try and memorize, okay, this solvent does that. You want to think about it in terms of the functional group. And so water, and again, we're getting a little out of order here because there will be a whole section on alcohols, but water has an OH group. So does, say, for example, methanol or ethanol, okay? And so the chemistry of those is similar. And so, if you have water in a halohydrin reaction, you should be able to sort of extrapolate to what you would get, say, if you used isopropanol or, T-butanol or something like that. Does that answer your question, Helen?
Yeah, so you're saying that in this case, it's kind of like water, like, or no? Is that not what you're
That's
saying?
exactly like water. Yeah. Yeah.
So we should, like,
Yeah.
for now, we should just think about it like with kind of like just use a heuristic and just say it's like kind of like water.
Exactly. Yeah. Just pay attention to, like, because what's involved, and I gotta sign off at 11:15 here. I'm sorry, guys, but we can pick it up later. What's involved when the water gets involved in the halohydrin, right? If we sort of zoom in on that, it's the OH group, right? I mean, it's kind of all there is in water, but it's the OH that's attacking the bromonium ion, right?
Right.
Are you with me? So yeah, so anything else, thinking by analogy, anything else that has a hydroxyl group could, in theory, do the same thing. It depends, it's going to depend on what else is there, of course, but certainly methanol, where I go from a proton to a CH3 group, ethanol, proton to an ethyl group, those are the types of changes that they're not going to affect the alcohol too much. It's going to behave very similarly to water. And so like seeing those types of connections, I think, is important. Yeah.
Okay, yeah. So I think this also clears up something that I was thinking about in class, because like to me, like from Gen Chem, like I always thought of like water as something very stable and something that, like, I mean, except for like in acids and bases, like, so I just like had trouble kind of like understanding like or internalizing the fact that like water was like donating electrons in some of these reactions. And so, I mean, I was just wondering if you could just clarify like why water is inclined to do that. Does it have something to do with like stability, or like especially in like the halohydrin formations, like why is water even starting to donate electrons in the first place?
Yeah, I mean, this is why I like teaching this class, is because you get these very like fundamental questions, which, I have to like think hard about it. It's I think the way to think about it is like, why is water participating? Well, what does water have, in its structure? So we've got two OH bonds, right? And we can look at a table. Those are very strong, about 110 kcals per mole. They're not going to do much. But then I've got two lone pairs. And if you think back, if you look in that last handout I made with the hyperconjugation, I think the last example is with a oxygen lone pair. It's drawn on an energy diagram, so you could see it. But those lone pairs are non-bonding. Okay, and so what does that actually mean? You know, it means they're kind of at this sort of this like neutral energy state. They're not high energy, they're not low energy. Okay. And so, but they want to get low energy, they want to become bonding. Okay. And so if there's a way that they can find their way into a bonding arrangement, they will. And so in this case, attacking that bromonium ion, making another bond is going to be favorable. So it's sort of like anytime you have, you know, maybe the concise way to answer your question is anytime you have a lone pair on any atom, it's potentially reactive. Okay. The question is that you need to sort of, you know, the resolution that you need to apply is, you know, well, how reactive, you know, and, you know, I mean, your question is a good one because in fact, water is stable, right? It's the, you know, the molecule of life. And when you run these reactions, you typically have to use, you don't use one equivalent to water, you use a large excess because it's actually not a great nucleophile. You know, those lone pairs want a bond, but water's pretty happy to begin with. So there's kind of like this qualitative analysis that you apply, and this gets at this issue of like nucleophilicity, which we'll talk about in gory detail, I promise, when we get to SN2 substitutions. But it's basically how easily will something give up its electrons to make another bond? And you know, water can do that. It's not great, but it's good enough that it can react with a bromonium ion. So it's sort of like this sliding scale of reactivity, and you sort of need to know where the atom that bears the electron sits on that scale. We'll define that when we get to the SN2 reactions. You'll see, but water is like it's just okay. So I don't know. Hopefully that helps. Yeah.
Yeah. So just to synthesize, you're saying that water is neutral, but in some cases that isn't enough, and it wants to be like lower in energy instead of neutral.
Yeah. Well, the lone pair.
The lone pairs on, yeah.
Are non-bonding. They'd love to get into a bonding orbital.
Okay.
Yeah.
All right. Thank you so much.
All right, I gotta run. I'll talk to you guys. I'll post. I'm gonna hang up, and once this is converted, I'll post it.
Thank you.
Okay. Bye, Christine.
Bye.